your shoes off and.
I don't know how well that would work. All right, well, I have 4 o'clock and what do we have? 70% of the class here? That's barely a C. Anyway, for all of us, I guess collectively. Well, anyway, that's okay. We've got most of us here, the majority, so I consider that a quorum. So I'm gonna go ahead and get started, guys. Good to see you today. Thank you for being here. I am recording this session, which might end up being useful this time. Yeah, so we're gonna pick up where we left off today, somewhere in the middle of class. I've got some group work. We're gonna practice some of the things with ideals and integral domains and so on and so forth. Picking up where we kind of have been leaving off. And then don't forget there's homework due on Sunday. As of now, that's the way I've got it set up. I should be around on Sunday for office hours. If you've got some things you want to talk about with the assignment, it's kind of just a review assignment about ring theory. So I'm hoping it won't be that bad. There are a good number of questions there, but nothing that requires a huge amount of ingenuity or creativity. So it's just a matter of kind of plugging through it, kind of getting these ideas back in your head again. I don't think it should be too bad. And then, yeah, we're actually really on good schedule so far. So I should finish this whole ring theory stuff before spring break, which would be awesome. So that when we come back, we'll have the whole rest of April basically and part of May to get into the field extensions and the Galois theory, which the more time we have for that, the better, right? This is kind of the big punchline at the end of the course. I'm actually ahead of where I was last year at this time. I don't know if I'm talking faster this year or or what, but maybe you guys are just picking it up that much more quickly or something. I don't know.
How big was your class last semester?
Oh, last year for this class? Oh gosh, there were 25 people in here. Yeah, it's huge. So yeah, so this has been kind of nice, I have to admit. Yeah, so let's go ahead and we'll get started. Last time towards the end of class, I had defined what an ideal is. I'm going to go ahead and use this same notation that is basically stolen from group theory. When you have a normal subgroup of a group, we use this sort of less than or equal to triangle notation. Ideals play the analogous role to normal subgroups. They are the objects that allow us to mod out and form quotient groups. So it kind of makes sense to actually use that notation because it is parallel to what you would have used in group theory. But this is not notation that you would see in most abstract algebra books. They tend not to denote ideals with this notation. But there's really no harm here. There's really not going to be any confusion with that. You obviously know whether you're working with groups or rings. So you can, I don't think there's any likelihood of being confused. But remember that an ideal basically is a subset of the ring. Non-empty subset if you want to get really fussy about it, but it's a subset of the ring that forms an additive subgroup. Of course, to be a subgroup, it's going to have to be closed under addition and closed under additive inverses, which is really just negatives. So you put those two things together, that really just means that I has to be closed under subtraction, right? You can combine those into a single thing. So this would be a closure. I'll just add that to the notes here. We did this last time. I'm just trying to get our heads back in the game here, right? So closure under subtraction is the first condition that we have to have for an ideal. The second one is a little bit motivated by trying to create a well-defined multiplication on the cosets that you're trying to form a quotient ring out of. And so I showed you that last time, but just to emphasize the condition here, it's really this closure under absorption that we're dealing with here. So for every element of the ring R and anything in the ideal I, so X belongs to the ideal, then it's not closure under conjugation like it was for group theory. Rather, it's just simply closure under absorption, right? So if I take something from the ideal and I either left or right multiply it by anything in the ring, the result needs to get sucked into the ideal I. Right, so I'll just call that closure under absorption. And again, where is this coming from? In terms of the motivation for this condition, it's really to make the multiplication of cosets well-defined in the sense that we kind of introduced last time, and I'll come back to that in a little bit. For the time being, though, I want to start off today with just really talking about ideals and looking at a few examples and non-examples, because I didn't have time to do too much on that last time. So are there any questions here? Just a quick little, just want to make sure you have the definition down, that the definition of an ideal is basically closure under subtraction and absorption. You got those two things, you've got an ideal. Okay, let's write down a few examples, get a little list here of some things that are kind of good to get this into our heads. So let's start with maybe an easy example. Whenever I'm looking for an easy first example in ring theory, I will almost always start off with the ring of integers. It's kind of my favorite go-to ring to work with. And let's try to make an ideal within that ring. So I'm going to define I to be NZ. And this would simply be the multiples of n. So n is just some natural number, some positive integer. We'll assume it's positive, it doesn't really matter. And so this is multiples of n. And so the claim here is that I is an ideal of R. I'm going to go right ahead and start using my notation right away here on this example. And so I'm going to prove this by checking closure under subtraction and absorption. And this is going to go really quickly. There's no surprises here at all. For closure under subtraction, well, I picked two things in I, right? So we could let I don't know, NK and NL, the elements of I, they have to be multiples of N, yeah? This would be where, just to be totally thorough about it, the K and the L are, of course, have to be integers here. And then I just have to subtract these. And so certainly nothing surprising about it, but just so we at least write it down once, I just have to convince myself that difference is still in I. It just means it needs to be a multiple of n. There's nothing more to that than simply factoring out the n. Okay, so pretty sure everybody can handle that. Because it's a multiple of n, it's back inside of I again. Now there is an and over here. Technically, the closure has to be on both the left and the right side. Oh, I'm sorry, I'm getting into the absorption part. My brain is working faster than my mouth right now. This is a commutative ring, right? So if your ring is commutative, then when I get to the absorption thing, I won't really have to check both conditions because everything's commutative under multiplication. But I should pause for a second. This is closure under subtraction still. Is everybody okay with it? Pretty easy, right? Okay, no issues there. So then closure under absorption, I don't know, I'm just gonna write it out. Closure absorption here. If anybody thinks of a nice shorthand for that, I'd love to know it. So I'll take that. So we take you know, let NK be an element of I as above. So we grab something from I, and then we just take anything in the ring. So I'll just call it R, just in the same notation as the definition over here. And then I just have to multiply these together. So then R times NK, right? We just have to make sure this is still in I. In other words, it still needs to be a multiple of N, which it clearly is. Okay, and so it's still in I. I don't need to check, as I've just mentioned, I don't really need to check that it absorbs from both the left and the right, since everything's commutative here. So that's a standard example, and we've actually got a ton of ideals in the real numbers, in the integers, right? A ton of ideals there, any multiple of any integer. Right, okay, let's do, let's, before I do another example, a quick fact here. Closure under subtraction and closure under absorption includes closure under subtraction and closure under multiplication. So what I want to point out here is that every ideal of R is also a subring of R. that's really just from definition. If you're closed under absorption, then part of what that would entail is obviously being closed under just regular multiplication. So nothing too surprising about that, but not conversely. Not conversely, and I thought maybe it'd be nice to give you an example of a subring that is not an ideal. So maybe I'll do an example here. So we'll get a negative example going, an example that doesn't really work as far as being an ideal. Or does anybody want to propose one? Can anybody think of an example that's closed under multiplication, but not under the full power of absorption?
You know, like matrices.
Oh, okay, great example. It's probably not the easiest example, but it actually is in my list here of examples. Let's go with that first. Okay, so let's take, I love it. Let's take the ring R to be, say, 2 by 2 matrices. I guess I'm going to do them over Q here. And then for my, well, I'm going to call it's not an ideal, so I won't call it I. It's going to end up to be only a subring, which is the set of, I think you said upper triangular, one of you said the upper triangular matrices. That's a perfectly good one to go with. So we could say A, B, and then 0, C, such that A, B, and C are rational numbers. While I'm doing this example, maybe see if you can think in your head of an easier example, and then we'll write that one down too, where we actually use commutative rings. But this is perfectly good because it's easy to see. Am I allowed to say that? I always get nervous when I say stuff like that. It's easy to see that S is a subring. It's closed under subtraction and multiplication. If I subtract upper triangular matrices or multiply them, I'll get another upper triangular matrix. Okay, so it's easy to see that S is a subring of R. However, it is not closed under absorption. So, however, if I took, you know, A, B, 0, C, and I multiplied it by anything in the 2 by 2 matrix ring, well, a generic element, we could actually give specific values for A, B, C, X, Y, Z, and W here if we wanted to be precise about it, but it's not really necessary. We can literally just do it using this notation. If we multiply this out, right? So AB plus BZ, sorry. And then AY plus BW. And then here's the kicker, right? The kicker is that the lower left corner is not 0. And so what happens is that this is no longer in S, right? So this fails to be in S. So S is not closed under absorption. This is kind of absorption from the right, but you could have done it from the left side as well. It wouldn't have worked there either. Closed under absorption. So S is not an ideal of R, right? So it's not an ideal of R because it's not closed under absorption. Any questions about that? Does that make sense? Can anybody think of another example of this that's even easier? Miguel?
The real numbers are subring of the complex numbers.
Oh, interesting. That wasn't what I was going to take. So I just have to convince myself. Yeah, that's certainly a good example, right? So the real numbers, R is a subring, but not an ideal. Of the complex numbers. I was actually going to use just the integers is a subring, but not an ideal of R. So almost the same thing, just at a slightly different level. So yeah, clearly these are rings. If they're rings, then they're subrings of anything containing them. But these won't be closed under absorption. So if you take a real number and multiply it by a non-real number, then you'll end up with something non-real, fails to be in the set again. Or if you take an integer and multiply it by something that's not an integer, you'll get a result that's no longer, well, it doesn't have to be an integer. So, you know, for example, if you took z to be, if you took the integer 1 and you scale and multiplied it by pi, well, you don't have an integer anymore. So these are pretty obvious examples as well. Nikolai?
If you go like the other way, it feels really wrong to say this, but like if you multiply anything in C by anything in R, wouldn't that make C kind of like an ideal to R? Even though C is
Well,
a subset.
C is not even a subset of R, so I can't think of it as an ideal of R. Right, the relationship there. So, you know, I always like to have, in fact, I should have drawn the picture, right? You have the big ring here is R, I is the ideal inside of that ring. So we're talking about grabbing something from in here, which I've been calling X, and something from out here. The thing that's out here could be also inside of I, but for absorption, it has to be possible to take anything from even the big ring R, and then the product of R times X is what you're looking at. Yeah. So, did you have your hand up as well?
I just wanted to ask, is there an example of a non-ideal subring of a finite ring?
Oh, I'm sure we could do that.
Like maybe for Z mod n?
Yeah, I think Z mod n might be a little tricky. But let me work on that. Maybe we could do something with let me think about that one. I'm sure that we could come up with an example. Yeah, definitely. So you're looking for a finite example?
Yeah.
Basically. Yeah, I'm sure that we can. Let me onto that in a second. I'll come up with something. Anyway, but these are really easy examples of things that are subrings but not ideals. Pretty straightforward. I guess we could also, if we wanted to, we could also say that Z is a subring, but not an ideal. If we wanted to have a non-field as our super ring, we could use Z of X, right? So now, again, you know, this is a subring, but it's not going to be closed if I start multiplying it by polynomials that have degree 1 or more. So that's another good example. Okay. Actually, the idea of polynomials gives me an idea. Ideal gives me an idea of another example I wanted to do. So I guess this will be example 2. Back to my original counting of examples here. So let's do this. Let's take the ring R to be Z of X. Okay, so I've got polynomials in my head now. Let's take Z of X, and then I'm going to let I be the set of P of X element of R such that P of 0 is 0. This would literally be the set of polynomials in R, just so we can kind of think of it a different way, that have no constant term. So in other words, so P of X has no constant term. That's why when you plug in 0 for X, the whole polynomial is 0. This is really just multiples of X, right? So we could actually write it one more time. This is just polynomials in R such that P of X has the form X times Q of X for some Q of X in R. Right, so this is the condition is if the constant term isn't there, then you can actually factor an X out of the remaining terms and be left with some polynomial of degree 1 less than P of X. That seem okay? Well, I claim that this is an ideal of R. So the claim here is going to be that I is an ideal of R in this case. This is the claim. Okay, so I'm going to try to show that now. Now I just have to show closure under subtraction and absorption. Okay, nothing bizarre is going to happen here. let's just check it, closure under subtraction. I've got to grab two things out of I. So let's just let, I guess I'll call them P1 of X and P2 of X. Let's let those be elements of I. And I actually think that this third formulation here, the third time I wrote it down, is maybe the easiest way to work with it in terms of trying to check subtraction. Okay, so of course, P1 of 0 is 0, P2 of 0 is 0, so I could just subtract. So P1 minus P2 of 0 is also 0. But I'm just going to instead use the condition here. And I'm going to write P1 of X as X times Q1 of X. And P2 of X, I'm going to write that one as X times Q2 of X. This is for some Q1 and Q2 in the Z of X ring. And now we just subtract, right? So we just subtract those P1 of X minus P2 of X. And the fact that I can pull the X out of the Q1 of X minus Q2 of X shows me that the polynomial P1 minus P2 has the right form to be in the ideal I again. Okay, so there's no surprises with that. It's closed under subtraction, yeah. Again, this is not the only way to prove it. I could just literally look at P1 minus P2 of 0. And I could, of course, distribute that into two terms, P1 of 0, which is 0, and P2 of 0, which is 0. 0 minus 0 is 0. It would look different on paper, but it's equivalently easy to prove. And then the other part here is the absorption, closure under absorption. Okay, so I'm just going to say, with P1 of X as above. Right, and let's just grab some other F of X, I'll call it, that lives in Z of X. So we'll just take an arbitrary polynomial out of Z of X. Well, then we just have to show the absorption here. Again, this is a commutative ring. So I can just check absorption on one side only. I can take F of X times P1 of X. And if we just feed in what P1 of X is, this becomes F of X times X times Q1 of X. And if I want to make it look pretty, I just factor the X out in front of that. And I'm left with the quantity F of X times Q1 of X. And anything that's a multiple of X like that is still in I. Very good. So we have the polynomials with constant term of 0 forming an ideal. Actually, I'll get to you in a second. It also, we could make other ideals by making conditions here that P of 2 is equal to 0, right? Or if P of 5 is equal to 0, any conditions like that would actually also have worked. Anything that would have been like closed under subtraction, obviously, and absorption you could use. Did you have a question?
Yeah,
Please.
the third way you wrote down I,
This one, yeah.
it feels like you basically defined it as R multiplication, right? Like you defined it as multiples of arbitrary elements of the ring. Is the absorption kind of obvious in that way, or?
I think it is. Actually, this turns out there's another way to write I. So I'm gonna put that as a remark right now. Right? What we can actually do, guys. You remember when we did subgroups, we were looking for sources of subgroups and we said, oh, I know a good way to make a subgroup. Just grab an element out of your group and form the cyclic subgroup generated by that element. That is actually basically what I is. It is cyclically generated by this X that you pulled out right here. So I make this remark that I can be viewed as the ideal of all multiples of X. In other words, we can actually write it like this. This is the notation for it. I know that when we did cyclic subgroups, we sort of use angle brackets for the notation, but typically with rings, it's written this way. There is a name for this. This is called the principal ideal. So we don't call it a cyclic ideal. Cyclic is the corresponding concept in group theory, but we would call this is called the principal ideal of R generated by, okay, so we're going to emphasize the generator here, generated by the element X. So this is called a principal ideal. And I actually think it might be worth it to put that as a formal definition into the notes here. So I'm going to come over here and give myself a little more room to write that down as well. So great point, Jaden. Yeah, this is kind of clear that these are always going to be ideals. You guys okay over there? That is the right way to spell it. That is the right spelling of it.
School, this is a math class.
I think I've spelled it correctly. If not, yeah, I'll have to go back and put an asterisk on my PhD because I didn't really do English to get this. But yeah, I think that's the right word there. Okay, so yeah, so just a quick, I'm gonna call this a definition. We may as well cover this right now because it is very important. Namely, let R be a commutative ring. And we're gonna take an element A out of R. And actually, this concept doesn't really require the ring to be commutative. But again, many times in our book and in this class, things are just easier to learn when we're assuming things are commutative. So we'll just do that for now. Then if we write down, an element A in parentheses like this, this is going to denote the set of R times A such that R is in the big ring capital R, right? This is called the principal ideal. This is called the principal ideal generated by A. This is the principal ideal generated by A. And kind of right along with that, if you start off with some ideal, so any ideal I that has this form, any ideal I of R is called principal if there exists a generator for it. So you have two ways of approaching this concept. You can either start with an element of the ring and just form the principal ideal that it generates. Or you can start with some ideal and ask, is it principal? And it is principal if there exists an A in the ring with I equal to the principal ideal generated by A. Okay. By the way, I may slip from time to time and use the same angle brackets that we used for subgroups. If I do that, no worries. It really is the same analogous concept here. So it's definitely not a problem. So like, for example, this ideal right here is literally all multiples of n. So going back to that example, this ideal that we just did in example 2 is also a principal ideal. Is that a hand?
Yeah.
Okay, please.
Sorry.
No, that's okay.
I keep looking at these definitions and it's called the principle. It's their only, I mean, we might have.
Well, this is well defined because you grab an element out of the ring. There's only one set that would consist of all the multiples of that element. And so that is called the principal ideal generated by A. It might be possible that we realize as an afterthought that that collection of elements could have been generated by a different element instead. So for example, we say, oh, well, what about all multiples of negative n, right? That actually would be the same set as the original one, but this is still one ideal. It may have multiple different generators, but it is the principal ideal generated by N.
Okay, so, so Z has a bunch of principal ideals,
Oh, this is like in group theory, you have a bunch of cyclic subgroups.
but
Grab your favorite element, form all the powers of it. Here we're grabbing our favorite element and forming all of the multiples of it.
Okay.
Right, so you have the multiples of 2 is a principal ideal. Therefore, it's an ideal. The multiples of 3 is a different principal ideal. It's also an ideal, right? Anything that's just multiples of any, whatever your favorite number is for N, you could make that principal ideal. Yeah, consisting of all of those multiples. Yeah, it's pretty neat idea. Yeah, David.
So you wrote, if there exists an A in the whole ring, that implies that we might not have A itself in I, even though it generates it, right?
Well, it will actually be in I, obviously, I mean, yeah, so
What
an
if it's-
ideal is principal if there exists an A. The A will be, what I've written here is not wrong, but I could have said, yeah, there exists an A in I. Because you can see that from here, right, the A does belong to I.
Well, what if we don't have a multiplicative identity?
Oh, so if we don't have a 1 that we can put here, so your concern is that, well, maybe we don't actually have A itself in the ideal.
I wouldn't call it a problem, it's just something.
No, I think we probably should assume that the ring has a multiplicative identity. I guess I didn't do that. But generally with ideals, that would be a natural thing to assume. Let me check on that, but I'm gonna go ahead and add that here with identity. This is how I solve all my problems in math. Just go back and add whatever I need to make things work out. Yeah, that it would be hard to do the theory of ideals for rings that don't have identity. Yeah. So, I mean, if the ring wasn't commutative, it would actually be easier because you could just say, well, if the ring isn't commutative, then we're going to form the left principal ideal, which would be everything in this form, which is separate from the right principal ideal, which would be things of the form A times R. So these things are generalizable, but we're gonna try to keep things relatively simple here.
If we're looking at a ring without identity, would it be more likely that we are picking an A in R or picking an A?
I would still like to leave the definition as it is here. That the idea would only be called principal if we can find that we allow ourselves the wide latitude of identifying any element in the ring that could be a generator for the ideal. So I'm very happy with the definition as stated, even if the ring didn't have identity. I've taught this class so many times, I don't think this has ever come up as an issue. So yeah, but normally the rings have identities, so it's not really an issue. Yeah, that'd be something to think about. Like, so if your big ring was just the even integers, right? Then like what do your principal ideals look like? So anyway, we'll think about that maybe after class. I'm not gonna get into it right now. One more thing to point out. I'm just going to state this as a remark. In any ring R, we always have two what are kind of considered trivial, I'll just say two ideals. There's always two ideals in any ring R. One of them is, of course, just 0 itself, which I can write as the principal ideal generated by 0. This would be considered what's called the trivial ideal. And then the other ideal that you would always have in any ring is the entire ring itself, which is clearly closed under subtraction and absorption as well. So this is there really isn't a name for this, but this is the full ring R. I'll just say it that way. So we have two sort of obvious ideals in any ring, and they are those two right there. So there will always be a couple of ideals that we can look at here. And that actually leads to something kind of interesting, which is the following fact. Stated right here. This is a very, very important fact. So this one will get used quite often. So I'm going to let I've learned my lesson now, guys. Be a commutative ring with one. I can't find this result stated in the book. I was looking everywhere to find it actually stated and I couldn't find it. So I'm stating it just as a separate fact. Might be because it's buried in the exercises. It's a reasonable exercise. So let's let R be a commutative ring with one. Then it turns out that, okay, so what if these were the only two ideals? So these are always ideals. There's a certain kind of ring for which those are the only ideals. Does anybody have a theory what that might be? What kind of rings would have only those two trivial types of ideals?
Symbol ring?
A simple ring, that'd be a great definition. That's not the right word. It's a word we've actually already used.
Abelian.
Oh my gosh, you guys, come on. Abelian is already definitely commutative under multiplication. So here it is. R is a field. That's the big word that we need here. R is a field if and only if. This is a two-way street. The only ideals of R are 0 and the entire ring R. So if the only ideals are 0 and R, then we will call it a field. But you know, simple ring would be a great idea, Larry. It's totally analogous to the way we talked about it in group theory. Okay, let's try and do the proof of this one. This is worth trying to write this down. So I'm going to start with the forward direction. We've got to prove this in two directions. So two things to prove here. Yeah, so this is super huge important. So let's assume that by way of contrapositive that we have some ideal other than 0 in the whole ring. Okay, so I'm going to assume that we have, well, actually, let's just do it this way. Let's just assume that I not equal to 0 is an ideal. Take an ideal that's not 0. And actually what I'm going to hopefully try to prove is that assuming that R is a field, so assume R is a field. So I'm going forwards here, and what I'm going to do is I'm going to claim that I is equal to R. So if you have a non-zero ideal in a field, then it must be the entire ring R. Okay, so to see that, what we'll do is, since I is not 0, I can pick an element out of I that's not 0. Okay, so let's let X not equal to 0 be in I. And does anybody have an idea? So let's slow down for a moment. A field. What is a field? A field is a commutative ring with one such that every non-zero element is a unit. Multiplicatively invertible, right? However you want to say it, right? So every non-zero element should be multiplicatively invertible, should be a unit. In other words, has an inverse under multiplication. Is there a non-zero element that we might want to play with right about now? Looking at our proof, we certainly started off with our non-zero X here. So we have an X inverse. So since R is a field, I'm going to write X to the minus 1 power exists in R. Now I'm trying to prove that I is equal to R. I is assumed to be an ideal. That means I is closed under subtraction and absorption. So would I be able to get any interesting elements to be inside of I based on what I have set up here so far? Say it again. The identity. the identity, because look, guys, X is in I. X inverse is in the ring, I sucks everything into it under multiplication. So if I've got X already in I, then when I multiply it by X inverse, the result is still in I, right? Is that a hand?
So since you have the identity in the ideal, you could basically multiply everything in the ring by it. You get that 30.
That's the next step. Yeah, you're thinking right ahead. Yeah, this is a beautiful proof, isn't it? Right, so the fact that X lives in I, then it sucks this thing into I under absorption. Okay, so since I is closed under absorption. Love it. Exactly right, it's closed under absorption. And once you have one in your ideal, guys, it's basically game over. Once one is in the ideal, then given anything in the ring. So now I'm gonna let R be anything in the ring. And I can prove that it lives in I. Why? Because I can write R as R times 1. I can imagine Jaden sitting over there thinking, oh, what if it's not a ring with 1? And they're like, oh, then I can't do this. Okay, the whole thing is not gonna make any sense, right? But that'd be an interesting question to ask also, like,
Well,
could
we
we
already
salvage anything from this?
We already know it's a field. So it has to happen.
Right, exactly. But we could try to change the statement somehow. Okay, anyway, we're gonna leave it the way it is. So we got that thing now. The 1 is in I, and so I multiply it by R. This must therefore be in I, right? So I picked an element out of R and I proved it was in I. Technically, that proves that R is a subset of I, but of course, the reverse containment is automatically obvious, and so hence R equals I, or in other words, I equals R. Beautiful. So if I have a field, then any non-zero ideal ends up having to be the whole ring R. Okay, so a field is very boring when it comes to ideals. It's like simple groups, right? Simple groups don't have any interesting normal subgroups, right? Other than the trivial subgroup and the whole group. So they really should call it simple rings. They did, it's just not historically the way it was ever discussed. So I guess that's the problem. Okay, let's prove the reverse direction. This is a really meaty result to know, and I'm gonna go ahead and prove the backwards part of this guy right now. Okay, and I'm gonna do this one by way of contrapositive again. So let's assume that R is not a field. What I'm gonna hope to do is create an ideal other than 0 and the whole ring. Okay, so to prove the backwards direction, I'm gonna suppose R is not a field, and I'm gonna try to create an ideal that is not the entire ring and is not 0. I'm gonna create a third ideal in this ring. Okay, so how do I do that? The right page of my notes here. Yeah, so if R is not a field, what I'm going to do is I'm going to sorry, I'm a little mixed up on where my notes are here.
You wanna call it security?
Yeah, probably.
Lost my notes.
Okay, so
You want something that's not true.
yeah, I don't know why. I don't understand my notes. I just want to grab a non-unit. Okay, so if R is not a field, then there exists some non-zero element A such that A is not a unit. So I'll just write A is not in the units of R. Does anybody have a proposal for the ideal that I'm going to create now that will not be zero, but will also hopefully not be the entire ring?
If it's not a unit, it has to be a.
Not necessarily. We can, in a ring, we can have elements that are not units and not zero divisors. Like in the integers, the number 5. It's not a unit, it's also not a zero divisor. There are no zero divisors actually in the integers. Yeah, let's be looking over here, right? We've just learned a great way to create ideals, which is to take any element out of the ring that we want and form the principal ideal generated by that element. So let's consider, I'll call it I, which is going to be the principal ideal generated by A. Okay. Now, since A is not zero, this ideal is not zero, right? So note that I does not equal 0. On the other hand, can I equal the whole ring? Well, let's try it. Okay, so if I was equal to the whole ring, then in particular, the number 1 would be in I, right? So then 1 is in, because 1 is in the ring R, so it would be in the ideal I if they were equal. But if 1 is in the ideal, then that means that 1 is a multiple of A, right? Because remember what this is, guys. It's over here if you need it. If you need it, it's right here. The principal ideal generated by A is just multiples of A. So if 1 is in I, it means that 1 is a multiple of A, right? So we can write 1 as, well, I'll just write it as R times A for some element of the ring R, right? Well, now you've got a contradiction because now you've got A as a unit, okay? So A is a unit, and that's a contradiction. That would be a contradiction. So if I is equal to R, we get a contradiction, thus I is not equal to R. So we have an ideal. It is an ideal, but it's not 0 and it's not the whole ring. And so that proves the negation of this side of the statement in the box. That's really the whole proof. Pretty neat idea. So in a field, you can't have more than 2 ideals. So if I ask you true or false, the real numbers have, you can find 3 ideals in the real numbers, right? It's false. The real numbers are a field, there should only be 2 ideals. So kind of a neat way to phrase it there. Okay, a couple more things here before we get too far along. Yeah, okay, come back over here. It turns out that some rings, okay, so obviously fields don't have very many ideals. There are some rings that don't have, that maybe have more than just these 2 ideals, but they don't have very many ideals. And so in fact, definition, if R is an integral domain such that every ideal is principal. So it's possible to have rings where the only ideals that are possible are just the ones that are principal. These are very, very nice. And it's generally, you can do it for general rings too, but it's especially interesting in the case of an integral domain. This is called a principal ideal domain. Principal ideal domain. So if you're working in a principal ideal domain, every ideal is very, very nice. And there are a couple of great examples of this. The first one is the integers themselves. Z is a principal ideal domain. So the multiples of n that we were looking at before, that is a great example. And the second big family of examples, so that's just one ring right there, Z itself. Another great example of principal ideal domains is to take any field and build polynomials over them. That will be a domain. There won't be any zero divisors in there, and it turns out that every ideal is principal. So f of x is a principal ideal domain if f is a field. So obviously, when you start with a field and you start building things out of that field, you will lose the field condition, which is the strongest condition possible. So you lose a lot when you build polynomials over a field. You no longer have a field, but you do have an integral domain still, and all of the ideals of it are actually principals. This is quite a nice observation, and somewhere along the line, I made a video for this. So this is actually a theorem. This is actually a theorem, and so for the proof of this, for the proof of this theorem, I'm going to have you watch a video. So I will send it to you. I did it on the glass board with the black background. It's really nice. So I'll say see video notes. I'll send that to you guys to watch over the weekend. In a field over a field, if you build the polynomial ring over that field, you'll get a principal ideal domain. Pretty nice. Okay, great. Couple more things before we take a little break here. Sorry, I'm a little disorganized today. I didn't quite, I was so busy with advising yesterday, I didn't really get myself as organized as I normally like to get. I wanted to mention about the kernel of a homomorphism. We said it was a subring on Monday, but actually it's better than that. It's actually an ideal as well. So it's another fact is that if F from R to S is a ring homomorphism, and we let K be the kernel of F, those are the, remember, that's the set of R in R, such that F of R goes to the 0 element of S. Then K is an ideal of R. So K will be an ideal of R. And that one is going to be, for the proof of this, I'm going to say, see group work number 7. We're going to do this after our break today. Problem number 2. So I'll let you guys check it. We actually already checked that it's a subring. So it's closed under subtraction and multiplication. And you just have a slight tweak to do to that to actually prove that it is closed under absorption. So that's not terribly difficult either. Okay. So then I'm going to ask you to recall, now that we've kind of reviewed ideals, some of the basic properties of ideals, we know what principal ideals are. We know that there are certain kinds of rings where those are the only ideals you could ever have. We know that in the case of a field, not only is every ideal principal, there's really only 2 ideals. That's super easy. The ideal structure of a field is super easy. But where did this whole conversation about ideals start from? It was really last class, the whole idea was to form quotient rings, right? So I'll just get back to that for a quick second. So I'm just going to recall that if I is an ideal of R, right, we can form the quotient ring, right? The quotient ring, which is R mod I, we'll use that notation, with elements. These elements have the form I plus little a, right? So we wrote this down, of course, last time. A is just some element of the ring R. So we form these cosets. They will be written additively. And what are the operations? The operations are that if I want to do addition in this quotient ring, so if I take I plus A and I add it to I plus B, well, that should just be I plus A plus B. And if I want to do multiplication of cosets, I plus A times I plus B, this should be I plus AB. So everything is kind of what you would expect and what you would hope would be the structure of the operations in the quotient ring. And it is a necessary requirement that I is closed under absorption in order to make this multiplication well defined. That was where the absorption condition sort of came in the first place. Okay. Are you guys with me? It's pretty reasonable. So let's just do a quick example of a quotient ring. I got to mod out by an ideal though. I got to make sure I do that. Oh, I got an easy way to do that. Just make sure I'm using, if I use a principal ideal, that'll definitely work, won't it? Take a look at this example. Oh, I love these examples. This is really cool. So let's do this example here. Let's take the ring R to be Z of X. And I'm going to make, we actually looked at this already, the fact that the multiples of X forms an ideal, and now we've talked about it in the context of being a principal ideal. Okay, so then that is closed under absorption and closed under subtraction, right? So this is an ideal, and so we can form obviously R mod I, which would be Z of X modded out by the principal ideal generated by X. Or, as another example, we could take the ring of integers and we could take, the multiples of n. And again, we can form, I'm just doing two examples here side by side. R mod I this time would be Z modded out by the multiples of n. The question that you're going to no doubt ask me, I mean, these are collections of cosets, right? These are cosets where, so everything has the form, in the first case, everything would be multiples of X plus little a, where little a is actually some polynomial. So it would really be some f of X, right? So you have some specific element out of the big ring R, right? That's how these cosets work. We grab an element A from the big ring R. So in this case, the big ring is the entire polynomial ring, right? So your cosets would look like, in a minute, maybe I'll write down what they would actually be. I don't have enough room right here, but they would basically look like the principal ideal generated by X plus some f of X. Yeah. Down here, every coset would look like, the multiples of n plus some little a, where a is an integer. Right. But the natural question is, to what familiar ring are these isomorphic? Does that sound familiar? To what familiar ring? To what familiar ring are these isomorphic? And while I'm erasing the board, why don't you think about it? We'll see if you have a theory on that.
What familiar ring?
Yeah, so each of these is a ring, it's a quotient ring. Just wondering, do we know, what would this be? Do we have an idea, in either case?
Oh, they're not isomorphic, it's the same thing.
No, these will be two different answers.
Okay.
Sorry, I'm gonna give an answer here, I'm gonna give an answer here. Two different things. Does anybody have a guess on either one of them? Actually, sorry.
The first one is the integer.
The first one is just going to be the integers. Correct. I'll come back to that in a second. This is probably the easier one. Yeah, this one, because if you just ignore the multiplication altogether and you just think of this as a group and you're modding out by the cyclic subgroup generated by n, it would literally be equal to Zn. Exactly right. Now, the question would be, how do you suppose you would prove such things?
First isomorphism.
The first isomorphism theorem for rings, Annen's version, of course. So we should definitely be thinking about that. Yeah, so the answers can be proved using the first isomorphism theorem.
Proved using.
Can be proving using. I really do need to go to an English lesson, apparently. Can be proved using the first isomorphism theorem for rings. That's exactly right. So I'm gonna state this theorem. Still doing okay on time? I think so. I'm gonna state this theorem and then I may not prove it because it's so much the same proof as what we had for groups. So I swear I've got to number my notes for next time I do this again. Oh, my notes are over here. So they're all out of order today. Okay, so yeah, so let's state this one, guys. The first isomorphism theorem for rings. And this will be Annen's version. Again, I'm going to again deviate from the book slightly on the statement to make what I think is a little bit better statement of the result. And so here's what it says, let F from R to S be a ring homomorphism. Okay, with kernel. I'll call it K. So we know what the kernel is. I stated the fact over there, and after the break, I'm going to have you guys prove that it really is an ideal of R. It's in the group work. Okay. Then R mod K, and mod out by that ideal, is isomorphic to F of R. Exactly right. That's exactly right. So, for example, to prove, as an example of this, again, I'm not going to prove this one. It basically gets proved the same way that the group theory version of this is proved. So you can construct a direct isomorphism between the two things. Of course, you have to check that it's well-defined because you've got cosets here. Okay, so you have to create this well-defined function from this quotient ring to F of R. That all works exactly like the group theory version. In fact, it might not be a bad exercise to just try to go through the motions of it. It'll be a good review of the group theory result as well. Take the proof that we did about 3 or 4 weeks ago for the group theory version of this and see if you can just write it all down with slightly different notations, of course, for the ring theory version. So proof, what do you say, omitted? And go on to an example here. We've got some great proof strategies going. Okay, so that's one thing I'd like to use. I was once did I tell you about the time I was asked to referee that a paper for a journal? And I started reading it, and I swear, whoever wrote the paper, they kept saying, "Oh, the proof will be in some other reference," right? Which was actually I started trying to find the reference, and I found out it hadn't come out yet. So I couldn't look up the proof. I was like, okay, well, maybe I'll just wait for the paper to come out. They usually give you several months to review these things because it takes a while. So I'll just wait for the paper to come out so I can check the reference. The paper never came out. I never saw the reference coming out. It's like, okay, this is an interesting way to do a proof. Proof by reference to inaccessible literature. Another good strategy. Yeah, right.
By staring into the.
I was waiting for the proof to come. I was so waiting for it. I was like, okay, he's gonna publish this thing. And in the proof of this, in the second paper, he's gonna make a use of something from their first paper. It's gonna be like one of these proofs. And if you're not paying attention, you could totally get suckered in. So, no, but I never did see the rest of that paper, so. I told the editor, I don't know, I don't think I would accept this one. Okay, I just wanna do this really quick, right, and then we'll take a little break. So to prove that Z of X modded out by the principal ideal generated by X is isomorphic to Z. The trick to doing this, of course, is we have to define a function, right? We want to use the isomorphism theorem. I'm gonna have to have a function. The function should go, so again, I'm always trying to figure out what should be the kernel, what should be R, what should be S, right? The left-hand side is where I see the quotient ring. So I'm probably gonna try to make my function go from R, which is Z of X. And I would like to map it to whatever f of R is going to be, but that should end up hopefully being on the right-hand side, being Z. Via f of little, okay, now I need like P of X. I need to plug in a polynomial into the function, and I have to spit out an integer such that the polynomials that will spit out 0, right, should be exactly the kernel that I want it to be, anything that's a multiple of X. So does anybody have a proposal for me here? I need a number. I need something that's going to be an integer. I think we've kind of already seen this today. It needs to be an integer such that the integer will be 0 exactly if we have something that's already a multiple of X. I'll have to think about it while I erase. I could write out P of X as like a whole polynomial thing. We really don't need to do that. We really don't need to do that. Any thoughts?
Could we do the A1?
Right? How about we just plug 0 into the polynomial? That gives me an integer, right? So, you know, if it helps, you can always kind of think about it this way. You've got some polynomial here. I don't know exactly what it is. But, you know, when you plug in 0 for X, you literally just get the constant term, right? So when will that be 0? Well, that will be 0. If the constant term is 0, then we're looking at polynomials of this form, which are precisely multiples of X, right? So that's exactly right. So this is the way to make this definition. You have to check that it's a homomorphism. You have to check that the kernel is the correct thing. And in this case, we also want it to be surjective. We also want it to be surjective. So let's go ahead and write a couple of those things down. I'll go a little quicker than normal through this, just because it really is a similar program to what we were doing for the group theory version of the first isomorphism theorem. So we check F is a homomorphism. And it's worth writing it out at least once here. So I've got to check, in this case, because we're in ring theory now, we have to check both the additive, my shoelace tied here. Got to check both the additive and the multiplicative property of a homomorphism. So we would have to check that F of, let's say, P of X plus Q of X, that should be equal to F of P of X plus F of Q of X. But let's just write it down. Essentially, I'm going to plug 0 in to everywhere I see an X. That's how we use this function. Well, but that's just F of P of X plus F of Q of X. Okay. And the multiplication is super easy as well. No surprises here at all. When I plug in P of X times Q of X, I just have to show that F respects that as well. So this would be this would be P of 0 times Q of 0. Literally put 0 everywhere you see an X. And that's just F of P of X times F of Q of X. And this is, of course, for all P of X and Q of X in Z of X. By the way, in a few minutes, I'm going to ask you whether it's really important if this is a Z here. Or could we do Q of X mod X and get Q? Could we do R of X mod X, get R, right? Whole bunch of things we could ask.
Of course, you just cancel the X's.
Yeah. I'm always afraid when I teach this class. I really hope no high school algebra students come in here. They're gonna be really mixed up. Okay, yeah, so we've got the homomorphism property. I need it to be onto, maybe I'll do that next. Doesn't really matter. So F is onto, check F is onto. Super easy, right? So you just start with an integer. So given, I'll just call it A naught, since it is kind of a notation for a constant term. Given that integer, then I've got to come up with a pre-image here. Guys, you technically don't have to show me your work of how you came up with the pre-image. Can somebody give me a polynomial that this function will send to A naught? Yes.
A naught.
How about A naught? Start with the constant A naught, right? We have F of P of X equals, well, it's by definition, P of 0. So you plug 0 in everywhere you see an X into the polynomial. Well, I don't see an X, so I just write down what's there, right? Which is A naught. Okay, so it's onto, and finally, we check the kernel of F, which is supposed to be the multiples of X. This is set equality here. I think I'm gonna try to do if and only if and do both directions of this kind of in one breath. So P of X is in the kernel of F if and only if, when I take F of P of X, I literally get 0, the integer 0. That's the definition of the kernel. This is if and only if P of 0 is equal to 0, which just means that P of X has no constant term. I guess I could write that down. P of X has constant term 0. This would literally be just saying that P of X is, you can factor an X out of it. So it's X times Q of X for some Q of X in Z of X. Beautiful. Well, that just means that that's just if and only if P of X is in the principal ideal generated by X. In other words, it's some multiple of X itself. Easy.
You want to write in, right? Not the.
Oh, element of, yeah, sorry. Thank you. Yeah. P of X is an element of that. So we've got the kernel, and so now the isomorphism follows directly from the theorem. Okay, so I'll just write that down and that'll wrap it up. Okay. Okay, so by the first isomorphism theorem, Z of X modded out by the principal ideal generated by X is isomorphic to Z. That's it. That's it. Because F of R is now just Z. The kernel is exactly the principal ideal generated by X. It just all flows perfectly. The second one, this one, same deal. I won't write it out. The proof is exactly the same idea. Start with an integer, reduce it mod n. The kernel will be exactly the multiples of n. Totally straightforward. I think there's going to be a homework problem asking you about homomorphisms from fields. Whatever, right? That's going to be really pretty straightforward because the kernel of this homomorphism has to be an ideal of the field. What are the ideals of a field again?
Zero or the whole.
Zero and the whole thing. If the kernel's the whole thing, well, that means everything got mapped to zero. That would be a trivial homomorphism. So if you start with a field, one option is that this could be a trivial function that kills everything, sends everything to zero. What's the other option? The other option would be the kernel is trivial itself, in which case that means that your homomorphism is actually injective, right? It's injective. And if you then sort of apply this first isomorphism theorem, your field will literally be isomorphic to its image. You're really modding out by nothing in that case. So there's really not a lot of interesting homomorphisms involving fields, just because there's not a lot of ideals in a field. That's kind of the idea here. All right, I think we are ready for a break. I think I've done all of that. I've done all of that. Sorry, I've been a little disorganized here. My notes are out of order and everything right now, so I'll try to fix that up during the break. When we come back from a 10-minute break, let's do a little group work here. And then I'll start talking about maximal and prime ideals. That will be the next thing we're gonna do. See you in about 10 minutes, about 5:25, something like that.
You mod out by something that's not X.
Oh yeah, you could mod out, actually, so here,
It's any polynomial.
any polynomial, you can make any, so all of the ideals in C of X are not principal. Because the fact over there was that if I have a f of X, capital F of X, where F is a field, all of the ideals are principal. Here, that's not true. You can make more interesting ideals that are not just generated by a single element. But heck, why don't we just mod out by things that are interesting here? And as long as you do that, yeah, you can mod out by anything you want.
Huh.
Yeah, it would be a matter of creating the what it's isomorphic to and trying to prove it. If you mod out by something like X minus A, it's still gonna be isomorphic to Z. If you start using things like that are a little more interesting.
Could you mod out by like R? Something that doesn't involve X?
Oh, you mean just mod out by
Yeah, by.
Oh, yeah, I could mod out by N here, then I would get to see N of X. Oh. Yeah, so you could get something very interesting. if you did that. So, sorry, I'm making my notes organized.
You're on.
Also, I did end up running out of space.
Oh, you did.
Here's my
I tend to
last
write,
page of notes.
I tend to write a lot, I'm
My
so
last,
sorry.
my last page of notes on the cardboard.
Oh, gosh, oh, wow, oh,
That's
wow.
dedication.
We need to take a picture of that, yeah, that is
It always
impressive.
happens.
That is
I
impressive.
was ready to go on the bench.
What type of notebooks do you use?
I use these, the white lines. It makes it really easy to scan when I do.
Jason, please pull up group work number
Lines
7.
don't show. But I like having it grid.
Yeah, I like the dot pads.
Yeah,
Or
the dot pads are-
I've got, that's how I have my homework and everything set up. It's black background, white gray dots, white, I write in white, it's great.
I tried the digital, but I just like physical more. I think I just like it.
I guess, I got that iPad and I was like, all right, I'm gonna give it a try. And I had to like force myself to give it an actual try. So I intentionally, I didn't bring a notebook and paper, so I had to use that. And I had it set up already, so I just had to like start writing. Then I was like, okay, I can do this, I can do this.
I always wrote too big.
Too big? Oh, on the digital? You can just zoom
I
in.
always zoom in.
Did you get signed up for the
Really
common
big.
enterprise class?
And then when I would try to write on.
Oh,
paper,
no,
I
no,
get-
no, that's right, you can't do it there. No,
I can't write this tiny.
You're so, but you're all set. Yeah.
That's why I
Pick that
really
button.
like,
The second it opens up.
Microsoft
I
Notes,
wanna take that.
Yeah,
because you can just zoom out forever and.
Sometimes you're not
and that wasn't good.
yeah.
So I like the Google Notes and Notability. I have to like, I have boundaries and it's.
Going off
like,
away from algebra topics
Yeah,
into
that's
something
what I always
else.
got stuck on.
I don't know.
I will say, I do like the texture of paper is much better.
Oh, the texture of paper on that, it's like I'm writing on a whiteboard. I love
I like writing on.
You wanna start working on it? I was gonna go to the restroom, but if you're ready, or you do something else.
Yeah, I actually have a question about the homework, just was something I was gonna ask Miguel about.
Oh, okay, you guys can talk about that. Okay, anybody want, here, I'll just. Whenever you're ready, you can start. I'm gonna go to the
I'm
restroom.
taking my
but
10 minutes.
Yeah, take your 10 minutes if you need to. I'm not trying.
I'll take a couple minutes.
Yeah, I just wanna get this passed out, cause I might.
You don't get one.
I was gonna say,
Oh, wow, I was
I
just-
feel like my hands were
Ah,
like.
I was asking Ken, is every finite through the main field?
Oh, there's your answer.
Yeah.
Yeah.
It's cool.
There you go. Your stuff.
Yeah.
I was thinking about that.
Also, like, I'm not gonna be here, well, Monday.
It's like, I feel like this.
Okay, I'll make sure to schedule
The
a quiz
ideals
that day.
work
Oh,
very
okay,
easily.
good. Okay.
It'll only be worth half your grade, don't worry. You can still squeak by.
Yeah.
No, thanks for letting me
If
know.
I can take it on Zoom, I'll take it.
There you go. So, yeah, no, that's no problem.
We're working much more with the infinite rings than we are with infinite groups.
And that doesn't.
It feels like.
Yeah, no, I noticed that too, because.
Although maybe we just haven't gotten to the finite part.
And I did everything else, I've never liked.
Well, you might be, I just told him I'm not gonna be here. I'm not gonna be here the Monday we get back from spring break.
Okay.
I'm going to see the eclipse. Yeah, and I know you might be into that too. There's last one for 25 years. Yeah.
Where's that at?
It's gonna hit Texas to basically New York. So I'm flying to Texas.
I was up in Portland when the last.
Yeah,
So I was actually right on the money spot.
yeah.
And we got to all sit out where they.
And it wasn't cloudy.
It wasn't cloudy, it
Oh.
was thick, it was perfect, it was clear. So I've seen the eclipse.
My family went to one, I think it was the one that started, because like, what is it, like. You know, here's the US,
Yeah, I can't forget the little.
Or whatever. and then that one went like this, right?
The panhandle is.
Is that what it is?
That one went like that, right?
Uh-huh.
So they went, my family went to Utah
Ah,
and saw it, and but mine, this one's like this. So we're going to Texas to see it, because the weather's probably gonna be clearer in
Yeah.
Texas
than anywhere.
than in Niagara Falls.
Did you ever, Ram, did you ever watch Oppenheimer?
Not yet, I'm so upset about
I watched Barbie.
Barbie
Not
was-
Barbenheimer.
Barbie was incredible.
I love Barbie.
You know
I thought it was great.
I thought it was hysterical too. You know, in the movie at the end of it, he's got that, I'm the hoodie.
Yeah.
And it says I'm enough on it. I have that hoodie. I got it for Christmas.
Nice.
It's sick.
My favorite scene in the whole movie was.
Yeah,
That's the entire thing. The
I,
entire setup is for one game of rock, paper, scissors.
I really like the, what's it called? The fight scene where they're like
Oh, yeah.
storming in and they're hitting each other with
Oh,
like.
he like blasts them down.
Yeah, like, he's just like this and there's like nothing.
Yeah.
He just get hits and he's on the second cup, he's like. It's so funny.
I'm taking up 2 spots, so you gave me an extra.
That's an extra one?
Thank you.
Sure.
Nikolai, let's get to work.
Hey, guys, before we do the group work, really quick, I just wanted to point out one other thing about this example I just did. You know, we talked about how this is isomorphic to Z. I kind of wanted, and we showed it using the first isomorphism theorem. But just so you kind of understand what's really going on here, the elements in this quotient group, they look like cosets, right? They look like, you know, the ideal plus some f of x. And this f of x is what? It's like, you know, I don't know, a naught plus a1x plus a2x squared and whatever, right? The thing is that when you mod out by something, just like we did with group theory, you're basically squishing this thing that you modded out by down to a single coset, which is identified with 0, right? In the quotient structure, like when you form R mod I, right? You're making cosets again. And everything that's in I, if I think of that as a single dot, becomes like 0. So everything in this expression that is a multiple of x becomes 0. When we pass to the quotient ring, it becomes zero. So all of this is somehow, I'll write some weird notation here. In mod I, it's like zero, leaving you basically, in other words, you're basically crossing it off. And so you are identifying all of these elements literally with the constant term. That's why it's the integers essentially here. Right? So whatever you mod out by, so here's something really interesting. Oh, you're gonna love this. Really quick, I'll write this in the notes next week. But whatever you mod out by, it's like you're setting it equal to zero. With that in mind, does anybody have a theory about what this would be isomorphic to?
C.
Oh, that was fast. That was fast. If you set x squared plus 1 equal to 0, right? It's like x is playing the role of I. So it's almost like you're setting x to be I. And that actually is a fair way of looking at it. And if you take the real numbers and you adjoin I to them, you essentially get the complex number. Isn't that weird? That is actually really weird. Okay. And actually, this is a field. So this is something else for us to talk about. I think I made a video. I'm gonna have you watch 2 videos. If you take f of x and you mod out by one of its principal ideals, which are the only kind of ideals it has, you'll get a field over here if presumably you've modded out somehow by what's called a maximal ideal. There's no other ideals. Remember, in a field, you don't have any ideals. So if this has no ideals, because this is a field, right? This has no ideals. That means that this thing has no ideals because it's isomorphic, right? So this has no ideals basically because you mod it out by something that's a maximal ideal. It's like as big as it can be. And the reason it's maximal, the reason you can't find anything bigger than this ideal is actually, it comes down to, and I'll talk about this in the video. It's the fact that this polynomial is irreducible over the real numbers. You can't factor it. You cannot factor it. So that is a result that's coming. I'm going to do all of that next week. This is just a preview to get you to come back 5 days from now and learn some more abstract algebra. It's really, really awesome stuff.
Wait, so if you mod out by any irreducible
Polynomial, then you get a field, and that is a theorem.
are they all C?
Oh, no, not necessarily, no, not necessarily all C, but you will definitely get a field if you mod out. But it's because when this polynomial is irreducible, it means that the principal ideal generated by it is somehow a maximal ideal. There's nothing, you've killed, right? You've got your ring, you've got your maximal ideal. There's no ideals above M. So that when you mod out by M, the structure you're left with here has no ideals in it, which means it's a field. No interesting ideals, which means it's a field. So this all needs to be written down and done very carefully and precisely, and we will do it next week. But I just had to get that in because I'm so stoked about it. Can you tell I kind of like this stuff? I don't know. They asked me to teach this class. I was like, oh, bummer. Shoot, I wish I didn't have to do that twice a week. No, this is great.
Did we ever define R adjoined with X?
No, not really. This is just, by definition, it's the smallest ring that contains all real numbers and contains I. So you just make sure that it's closed under addition, subtraction, multiplication.
There was something I was reading in the book that was like a super concrete definition of a group adjoined with X, and it was like X, it's a group.
There's actually something called a group ring.
Yeah,
Maybe that's what you're looking at.
maybe.
Anyway,
group.
guys, go ahead. Take this handout. You should have it in front of you. Grab 2 or 3 people and see what you can do with these 3 problems.
Join me, someone.
What's that? You've got to be adjoined to someone.
Yeah, I said join me, someone.
Yes. And so everybody should work with at least one person.
We've
only-
X.
Yeah, Jacob and Holly, you guys come over here if you want.
Like that.
Well, the one I read was like X is just a new element, you call it.
Yeah,
X,
notes are good.
And it's in the set.
You guys mind if I let Jason kind of be with you guys today? Jason is in Zoom. Jason, you gotta help these guys out.
You get the party with us.
So Cole and Jade need your help, so, yeah, we can get the chat open if we need it. Oh, he's got his camera on.
Hi,
now.
I'm out right now, yeah.
Okay, great. All right, so this is group work number 7, which is in.
Yeah,
Canvas.
I've opened it up, yeah.
Or maybe these guys can write it on the board if they can help you with that.
Where are you?
You at school?
Yeah.
Alright.
What's up?
Whatever,
Don't worry about it, it's alright.
just curious.
Fine,
Alright.
No, it's irreducible. Yeah, that polynomial is irreducible, so it forms a maximal. I have not defined that. yet.
Yes, show everything to you.
Not out by it.
Has a multiplicative. Maximum.
Zero, set.
Yeah, there's no ideal strictly, well, a maximal ideal is one where, so M is maximal if there is not a system I between it and the whole.
Is what?
Fine.
Fine, yeah.
So it's gotta like loop around, right?
So you might have thought about. Yes, so that is actually not.
I mean, that helps.
You already thinking about something.
Right.
pretty different. Anyway, but
So if C.
this is for next week, right now, I want to.
Let's just say, I agree with the that was a generality.
Right. So that was all they.
I'm using so instead of my implication symbols, but
No worries.
That works.
It works for me.
I minus J.
Okay, yeah, there you go.
You're right.
Hooray.
But R is in integral domain. See, I hate writing.
I love writing.
Or. If this is 0, then this is a 0 divisor. And we can't have that, because we're in integral domain, right? So. This.
Wait.
So we just want to know that every non-zero element.
Why is that as your?
Oh, A is not 0, so A to the 1.
Start with a
It's not.
non-zero.
Yeah. So you have A times A to the something.
Right,
Yeah.
A to the 1 times A to the J minus 1 equals
So it's
0.
finite.
And again, we're in
So
integral domain,
this
so
doesn't go on
we
forever.
can't do that.
Right.
But then,
Eventually.
okay,
you gotta
so then
start
this gives us that.
One, it's like
And of course, like,
original infinite version of.
maybe one of that.
All
Y
these
minus J is
digits,
greater than.
but you only have finitely many things that they could be considered.
Right.
Eventually.
So we have a power that.
Right, so see if you could work with that. Okay, now
Yeah,
come back.
we have a power that.
Yay.
Let's see. How we doing?
And we know that this.
Right.
I can't.
Like, this is finite because it's in a finite set.
Yeah.
No.
Okay.
No.
I just wanted to write this down distinctly that eventually the powers are gonna overlap.
Yeah, and that works for all A.
Actually,
Yeah, perfect. That's what we wanted to show. So everything in the ring of the unit.
Excellent colors that I'm trying to use. Yeah.
Problem is not going to be that hard.
Yeah.
You really need to show that, you need to show that,
Can't use blue, can't use pink, can't use.
XR
Can't use
and
brown.
then Y, like, make K,
I can't see the color.
XR and right?
Yeah, that's the tricky part.
And R, and then.
Yeah, I would say that looks almost brown.
I'll use a little K usually.
I mean, it's not the tracer.
No, I'm not. I look at the
I'll use
flowers.
R and R, that makes sense. And K,
But I
that would
can't
make
like.
sense.
distinguish like yellow.
But that's the same thing. As showing that f of r k is 0, right?
Wait. What are we doing again? A is ideal.
Solid color.
The way we're doing that is that anything.
Just thin little lines.
Let's write out what the definition is. So
Yeah,
RK,
okay.
that's the absorption definition, right? It's in K if and only if RK is 0.
Like, oh, I'm standing here. Just went on
But
I don't know if you're, are you going into teaching?
I say,
No? Oh, man, I didn't know what field you're going in. If you're going into teaching, don't be so.
He's not going to, he's going into.
so,
Yeah. All right, anyway.
of RK.
My hint here, you wanna know we have a field, so let's.
That thing gets sent to
Any
0
non-zero element
equals f of r 0 equals.
And you have to show that it has a multiplicative.
Yep, and 'cause we already did the subring part, right? We already showed that the kernel is a subring, so.
This one.
It all
Yeah.
is that background.
Yeah.
with communication.
So
the only other field that we are-
So it absorbs all.
Zero, right, but then this is.
Zero, which means that R.
Oh, so remember.
I did it backwards.
Yeah. I don't know how I do that. Okay, and the last one, this might be a little more interesting. A ring homomorphism is an ideal S, prove that you can pull that.
Right, everyone's that's a field.
Yeah.
Right, so here, we're just taking powers of A, but the point is.
I tried to
F is finite,
like,
and
oh,
all
we
of
need
these things are in power.
For A,
Okay,
we
so
need
how are we gonna do this?
something.
Really go
Let
Form of it.
X be equal.
But I don't think we can.
Well, let's make it into G.
I'll come back, yeah.
Okay, so.
Yeah.
Then, yeah, I might be stuck there.
Can you try that?
Of X.
Let's assume.
Anybody else?
Yeah, so what's the most you could factor out of J is a small?
Like I said, I don't know.
So.
I don't know if I want this.
All-
Can we see that? Okay, let me just,
But it is.
There we go.
But-
We're getting some-
that's what, yeah, that's what Cole's doing. So he's doing the last one, so it's kind of hard. Actually, you know what I could do? You know what I could do?
And it's an interval domain.
That'd be a little bit.
You know,
So.
Yeah, this is a good English thing.
And,
R.
Yeah.
Okay.
So-
So A is not zero. None of those are.
F,
Now you're. Now you're.
F,
I'm not really sure how to-
R.
Most,
That's
I don't-
F,
I don't think
X.
Checking.
Is
Absorption.
Yeah.
Okay, is Jason following along? Okay.
X.
You guys did it work out over here?
The RX is in the pre-image of A.
In parentheses, that we're thinking, oh, all I can do is like.
I feel like all these proofs are the same. You bring it up to the code domain, you bring it back down to the domain. Alright, that's absorption. You're the one to show that it's still a, well, we might be inclined to say, well, if it's a ring homomorphism, it's a group homomorphism, if it's an ideal, then it's an.
Oh, yeah, there we go.
So you pull it back. Yeah. So the other one is nice. It would literally be the group theory.
If is a
Ring have an integral domain.
Oh, yeah.
Is a product of zero.
is a group.
Yeah, this is zero or this.
Right.
But this one is not. Gonna be similar. Right, the A is not zero, so this is not zero. So that means.
So-
this is zero.
Right.
Readment of J is an additive.
Right.
Try to show that A is unitary.
Yeah.
So A times something.
Yeah. Like we just ignore all the multiplication, right? No, it's all group stuff. Oh, you don't want to do that.
There we go.
Yeah. That's the nice thing about doing groups first, I guess, because,
A times.
yeah, a lot of the stuff becomes really nice.
We did rings first and then good groups and then
Now we're
back to
You could say it
rings,
that
but
way,
now we're
yeah.
doing it the group way.
Yeah,
Uh,
the last one isn't too bad.
no, no, it shouldn't be. So, yeah, these are really not that bad.
The nice thing is, like, you show absorption,
Mhm.
and then you can just use everything as a group.
Right.
And like, oh, we already showed that pretty much is a subgroup for subgroups.
Exactly, exactly. So
Later,
Yeah.
you were gonna say.
do you want to go first?
No, I just had a question about something
Unrelated?
that we covered earlier.
Oh, well, do you want to ask it?
Yeah, so.
Otherwise, I'm gonna give you another problem to solve.
We talked about, Check my notes real
While you're checking your notes, I want to write a question. This is not on the group work, but it's a natural follow-up right now. True or false? If F from RS is a homomorphism. And I is an ideal of R, is F of I an ideal of S. So in other words, if we take, instead of taking pre-images of ideals, if we take images of ideal, if we go forwards, so starting with an ideal in the domain, would the image of an ideal still be an ideal? That's an interesting question. And
So it's really the multiplication that we have to worry about, right?
the absorption.
Yeah.
The absorption, yeah. Yeah. So, anyway, do you want to think about that now, or do you want to do this?
I do want to think about that, but I also wanted to ask, if we take up the commutative requirement for F being field if and only if the ideal,
Ah,
because I can see that
then it would be a division, we call it a division.
it'd be a division ring.
Right,
Okay,
right, so
okay.
division, that would be exactly the condition.
So R is a division ring
Right.
if and only if the only.
And I would have to be precise that, well, and I
So,
guess.
in other
so it's
words-
two-sided ideals.
In other words, the only ideals being 0 and R
Right.
does not guarantee commutative.
I have it over.
Oh, definitely,
Okay.
definitely.
With our,
Yeah, that's definitely true. Okay, nice. Did you guys get everything to work out? That looks great. And now we're working on the cuddle one.
just gonna let.
And that's good. Yes, I love it. I love, yes, so we're for RK. Nice job, nice job. Try. You get good.
I'm gonna see if I can.
This should be. So there. So, is this is.
Unless it's not a problem.
Well, so.
Yeah.
Yeah. I mean,
Well, so, because this is a finite list. I mean, that's what this, if these are, if this is equal to 0 when I subtract it, it means, so such that.
Right, okay, so the question is that we didn't pull some
This is an infinite,
F
so.
R.
Right, so eventually there's some A
need
to
to
the
multiply,
I, some A to the J.
like,
Well,
S times F of X.
Well, not necessarily equal to A. I don't
X
like-
and I. That's the question.
All I know is that two of these things.
The issue is, I don't know if F is
Maybe,
surjective.
maybe there is
Or
nothing.
there might not be something in the domain that maps to this, and then we
Somewhere
can't
something has to
bring
agree.
these together, you know? Do that, that's Jacob.
So can you have a, Counter.
If I'm A. and
you have
you're
a
A,
non-surjective F,
it's A cubed.
that's a homomorphism,
To the fourth,
not the trivial
So
one.
on, right? But the only element.
Well, that would be
that
nice.
is equal in this room.
Because that would,
Eventually.
if it's trivial, then 0 is always.
Oh, okay. But it might not be me, it might not be you, it might not be.
Sorry, I thought trivial,
Is equal to A to the.
I meant the trivial homomorphism.
yeah, sorry, I thought about it backwards. I thought like the identity map. I don't know why I thought that. I thought we defined the trivial
Or
home.
we are elements.
Okay.
Is this-
Wait, no, I think we did. Maps everything to identity, right?
That's it. Okay, yeah, okay. There's a conflict of what identity means. The identity map could mean it sends everything to itself, or it can mean it sends everything to the identity. That's
No.
funny. I never thought about that.
No, you're right. The identity maps does in fact send everything to Excel.
Yeah. I mean, the identity function, right? But it
Yes.
could be thought of as mapping to the identity, which would be the opposite thing. I mean, I'm thinking of something weird like the even integers.
This is close, I mean.
That's, I mean, that's
Yeah,
a pretty
let's-
ill-behaved ring.
Let's take the even integers and let's map the integers to the even integers.
Right.
Well, if everything in this list was always giving me something new and something.
Okay.
Oh, wait, the integers is,
Infinite list contained in a finite set. That can't happen. You can't have something infinite. As a subset.
so what about like 3? I think that was the word. Maybe we need something that's like, because the integers and the even integers are like.
Be too bold to say exactly when.
Definitely need it to not be subjective.
But
Yeah.
actually,
But then.
some of these things can.
Maybe the integers to like a finite set.
If they weren't,
Go back to the.
right, then because.
it'll
of
be
stuff like
harder,
that,
yeah.
they're
It makes it-
forever
That makes it hard.
Not be
An
certain.
infinite, a finite set to an integer. Maybe C mod n to the integers via.
I don't think the operations will play nice though.
Oh, yeah, we have ism.
So maybe this will work.
So my cultivation.
And,
that-
F of N is 4. Is that a homomorphism? Okay. And.
This one the opposite.
Like some-
We don't know what it is, it's not necessarily,
Equals.
we're not gonna necessarily get
Plus
back
four
to
m, that works.
That's true,
A
right?
multiplication.
but we're gonna find a. Just being very.
4 and M.
Being very.
Oh,
We're not gonna get a 4N, 4M.
Some power
Okay,
and
okay.
back to some other power, we try to be too greedy
greedy
and say, oh, well. That's one, and so therefore.
It's squared.
Which is just gonna apply to.
Addition will fail us.
Yeah, and subtraction.
Yeah, it's hard to think of things that preserve additivity and productivity.
Yeah, because of how we started writing out.
And you wanna start with weird stuff,
That
right?
looks like it hints at that, right? So then what you do is you're increasing the power. The pre.
If we go the other way,
This means.
Eventually.
Yeah.
Well, hold on.
J.
Hold on. X is in F of I, right? The problem was we can't pull the F back and get something, right? But we, or is that for the X or is that for the X?
the issue is we have S times X, okay, that's S times F of.
Something.
I for some I.
Yeah, we know that exists because X is in.
Yeah, and we.
Okay.
In.
Needed to be surjective, I think.
Right, so I just as a quick counterexample, I could. Is how can you fix the statement so that it is actually something that is true? So.
I think it has to be surjective. That was where we had a problem in our proof.
Right. Sorry about that.
So I'm.
Congratulations, it looks like your host.
Yeah, you've now stolen my class.
You're a host now, though, I think.
I mean, we're done anyways.
Yeah.
Yeah.
We're gonna.
Did you see the last part? So, yeah, no, I think you can see it, yeah. It's not true, because you run into a problem with you can't find a way to talk about this being in here. Because your function might not be surjective, right? You would want to turn it to something like f times f of I, and then maybe write like equal to like f of, I don't know,
F of R.
A or R, yeah,
R, yeah.
f of I, and then it's like, oh, but I mean, that's f of AI, and then you're done. But you don't know if you can do that, because
Yeah,
it might,
yeah.
you might not be able
Yeah.
to A that maps to S, right? So you have a hard time there, but
Do we have an example?
Bring that back around. This is in.
if I can rewrite what I erased, yeah, if you have it going into the codomain, then you're
And
good.
then.
That'll be an ideal for codomain, because then you can do that, or if it's surjective, yeah, same thing.
Subtraction is just kind of like.
And then another example was this right here, which, yeah, you can
Showing
see.
it's an additive.
Theta R, map everything to itself, it's like, okay, take your ideal to be the entire integers, that's not an ideal in the real numbers, right? As we
Yeah.
have today, I think, it doesn't absorb all that multiplication, you can just throw pi in there, and it's like, oh, you're not doing anymore.
Yeah, I just,
Suffering.
you know, started the semester, I like.
Because.
Yep.
Just no relative.
But yeah, we're about done anyway.
But by the time you get the ring, it really is more. Right.
Good job. Did that all end up making sense?
Yeah,
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 you guys?
I tried to re-explain it to Jason, because he might not.
He might have
Yeah.
got cut out on a little bit of that. Okay, whenever you guys want to take off, it's basically
Yeah,
time to
5:15.
call it a day, but thank you so much.
Mhm.
Jason, I'm gonna end the session now. Bye.
Yeah, bye, bye. Thank you.
You're welcome. Bye.